Welcome. I'll be showing you our results on dynamic soaring flight tests that are performed as inclined circle trajectory in open fields. This work is a collaboration between INAC and AIAA with the authors myself Murat Brons, Nikola Gavrilovic, Antoine Drouin, Gauthier Hattenberger, and Jean-Marc Mosqueta. Previously, we have presented similar flights at the leeward side of a ridge, while the aircraft flies through the shear layer. And now I'll be presenting inclined circle trajectory in an open field, flat terrain, flying at different altitudes. Compared to our previous work, we have implemented constant airspeed flight mode, improved our guidance method to parametric vector field guidance, characterized the aircraft's propulsion system from flight data, and also added two new ground-based methods for wind measurements, which are used as ground truth. What we are seeing here is the manual flight of an extreme demonstration of using wind gradient in atmosphere as energy source for these gliders. Unfortunately, the technologies that we currently use are not capable of keeping up with such high-speed flights and agile maneuvers autonomously. However, understanding the difficulties in energy extraction mechanism and obtaining flight data will move us forward towards future high-performance vehicles. The test equipment includes the airframe, an ordinary computer to be used as ground control station, the small XP telemetry modem seen on top of the computer, RC transmitter for safety link in case of emergency, and an optional antenna base for differential GPS setup. The airframe is a composite glider with 1.5 meter wingspan and it weighs 1 kg. It is equipped with an electric motor for easy launch and recovery. We used the well-known Paparazzi autopilot system in our work as it offers a flexible architecture, powerful flight plan language, and handles both the ground segment, airborne segment, and the post-analysis of the flights. Detailed information can be found in the link below. The challenging measurement of angle of attack, side slip, and the airspeed has been acquired with a custom multi-hole probe called Smart Probe. In order to have wind measurements as a ground truth, we used a mobile LiDAR system called Wind Cube. It calculates the wind vector components with a dedicated signal processing algorithm by using the measurements values of 5 consecutive beams. The total reconstruction occurs at 1 Hz, and we gathered information from 20 points simultaneously, starting from 40 meter up to 170 meter. An example of 1 hour long averaged wind speed measurements are shown on the plot in red dots. As the wind cube cannot cover the altitude range below 40 meter, a lightweight system is deployed for wind estimation based on quadrotor flight attitude. A vertical wind profile estimation generated during ascending and descending phase is shown in the plot. The presented system collects and stores data in 5 different locations. The low frequency data is logged under ground control station computer. A high frequency log is stored inside the SD card of the autopilot. Smart Probe also logs the sensor data on board its own SD card at 500 Hz. Mobile LiDAR logs are the wind vectors for different altitudes reconstructed at 1 Hz, and the quadrotor flight logs, including its full state at 10 Hz, are located also in the ground control station computer. Now let's have a look at the flight tests as the main objective of this work. As a full representation of the whole flight campaign, we have identified 3 different flights from 2 separate days. You can see the flown trajectories of each flight on the Google Earth representation. We will present the real flight's measurements now. However, I want to mention that the measurements taken during the flights are very noisy, related to the nature of the sensors used. Therefore, they have to be filtered before being used for anything useful. Researchers interested in a future simulation work should consider updating their sensor models accordingly. Now let's have a look at flight number 4, which is shown in dark and light blue. You can see the flight altitude plot in gray and the selected flight segments in colored. The first segment contains the level flight flat circle at constant airspeed. The objective of this segment is to obtain the nominal performance related quantities such as power consumption, average throttle, specific range, etc. Following this segment, the flight altitude is reduced and inclined circle trajectory tracking is activated. From the table, we can see that the glider's average airspeed was almost constant around 16.5 meters per second at each segment, which was the set point. During the first segment, the flat circle, the average throttle was 40.4%. All of the other inclined circle throttle values are lower. If you concentrate on the power consumption at each segment, it is also visible that the inclined circle trajectory requires less power. Having a constant airspeed and constant angle of attack throughout the whole flight segments, including the flat and all inclined circles, ensures that the vehicle is performing at similar finesse ratio. Therefore, the performance gain observed during the inclined circle trajectory must have come from the aircraft's interaction with the wind field and the apparent horizontal wind gradient visible in the body axis. For an aircraft capable of flying 1 hour in cruise condition, the shown performance increase corresponds to an endurance augmentation of 10 minutes in the worst case and up to 20 minutes in the best case scenario. A consecutive flight is performed to verify previously obtained results. You can see the flight altitude graph of flight number 5 in gray color and the two selected flight segments in blue and orange colors. It can be seen that the flight altitude has been kept constant and at low altitude. The particularity of the second segment, shown in orange, is that the average altitude is 3 meters closer to the ground compared to the rest of the flight. We can clearly observe the same low power consumption and low throttle usage in these inclined circle trajectories compared to the flat circles as well. These values increases the evidence to our previous observation, that is, inclined circle trajectory can be flown more energy efficient than the flat ones in the presence of wind. More detailed analysis of each segment can be found in the paper like the one shown here. We have observed a power consumption reduction and range efficiency augmentation once the inclined circle trajectory moved closer to the ground in flight number 5, even though there were no significant wind gradient measured. In order to further investigate the mentioned observation, another flight test is conducted on 22nd of April 2021 named flight number 7. As it can be seen from the table, all three segments require less than 31.5% average throttle. Average power consumption values are also lower than the flat circle trajectory. These values once again increases the evidence to the previous observation, that is, inclined circle trajectory can be flown more energy efficient than the flat ones in the presence of wind. However, the correlation between the inclined circle altitude and the extracted power is not very easy to generalize between the flights, as the third segment, which has higher altitude than the first segment, has similar throttle and power consumption values. As a final discussion and future work, we can mention that it is possible to measure and visualize the wind gradient-based energy extraction during flight. We have observed an increased efficiency during inclined circle trajectory compared to flat altitude hold circles in the presence of wind, even though there were no significant measured horizontal wind gradient with respect to altitude. We measured a potential increase of 10 to 20 minutes of endurance for an aircraft that can only fly for an hour. We also observed that the circles close to ground performed more efficiently. For future work, we will further verify our statement on the efficiency with more flight tests and hopefully work on the autonomous decision of circle center point and inclination angle. Thank you very much. please check out the link.